Okay, before I show you a PicoSoft control simulation, I will describe the requirements of my hypothetical conveyor system. Here we have a diagram of the system that I created in AutoCAD. This shows a top view of the system. The key requirement is that we have to move manufactured parts from a production line conveyor, which you see on the left, to a FANUC robot that will be performing automatic part inspection. The robot will pick up and place parts it receives from the conveyor system into a special test cell or load cell. The test cell will then test a part and send a measurement signal back to the robot, at which time the robot will move the part back onto the conveyor and turn on either a good part or a bad part signal. If a good part signal is received, the conveyor must move the part down to a packaging line. If a bad part signal is received, the conveyor must then divert the part to a separate bad parts line by activating a diverter gate, which will be connected to a pneumatic cylinder controlled by a solenoid operated valve. Now, if the robot should temporarily go offline, there will be no good or bad part signal, and the system must then divert the part to a separate reinspection line by activating a different diverter gate controlled by another solenoid. The system is to assume that the robot is offline if it does not receive a signal from the robot within 40 seconds. This conveyor system will be controlled by a Pico controller, and the controller will have 7 different inputs. You can see the inputs marked on this diagram. We have a system start button, stop button, and a reset button. We also have 2 photoelectric sensors. One senses when a part arrives from the production line, and the other senses when a part has been positioned in front of the robot. We also have the good part and bad part input signals, which are digital outputs from the robot. The Pico will also be wired to 4 different output devices: a system run light, a conveyor motor, and 2 electronic solenoids that will operate the control valves connected to the pneumatic cylinders driving the 2 diverter gates. Next, I want to show you a diagram of the individual steps of this conveyor process. I used these steps in developing the Pico ladder logic. You can think of each step as a time period in which the system waits for something to happen. Normally, a step waits for an input signal to turn on, but a step could also be waiting for a timer to expire. In this diagram, you can see that each step has a name and a list of active outputs. These outputs will be turned on as long as the step is active. This diagram also shows which specific input or timer causes the transition between steps. For example, when this input, photo I1, turns on, step 1 ends and step 2 begins. In the ladder logic that I developed for this process, each step you see here has an associated Pico marker value. A step is active if its associated marker is true. In this system, only one step or marker will be active or true at any one time. Now I'll use the PicoSoft simulator to show you the active steps of this conveyor process, as well as the output signals that are generated. Here you see the markers I have used in the Pico ladder logic. The marker names include the process step number that each marker represents. These last 4 markers are wired up to be the same as the 4 process outputs. I created these markers in order to show the outputs without having to switch between the Pico marker display and the output display. Okay, now I'll hit the start button and we can see that the system run light is turned on. If we look at the step markers, we see that step 1 is active and we are waiting for a new part. If I trip the first photosensor, you can see that step 2 is active and the conveyor motor has turned on. If I trip the second photosensor, you can see that step 3 is active and the conveyor motor has turned off. We are now waiting for the robot to send us a signal. If I turn on the good part input signal, you can see that step 4 is active and the conveyor motor has turned back on. The motor will now stay on for 15 seconds in order to send the part completely down to the packaging line. Then the motor will turn off and the step 1 marker will become true. Now I'll perform the same sequence, but I'll turn on the bad part input signal. You see that step 5 is active. In this step, the conveyor motor is on for 7 seconds to move the part down to the first diverter. Then we go to step 6, where the motor is off and the bad part diverter solenoid is on for 4 seconds to push the bad part off the line. Then we go back to step 1. Finally, I'll perform the sequence again, but I won't turn on any input signals from the robot. So we will be simulating when the robot goes offline. For this demonstration, I've set the timer that would normally be 40 seconds to only 15 seconds. Next, we'll see that step 7 becomes active. In step 7, the conveyor motor is on for 11 seconds to move the part to the second diverter. Then we go to step 8, where the motor is off and the reinspect diverter solenoid is on for 4 seconds to push the part off the line for reinspection. Then once again we are back in step 1, waiting for another part. Now I'll demonstrate what happens when I stop the system. Let's say we detect a new part and the conveyor motor is on. If I hit the stop button, you can see that step 2 remains active, but both the conveyor motor and system run light are off. If I hit the start button again, both the motor and the run light turn back on. If the system is stopped, we always remain in the step we were in. A reset push button can be used to override this behavior and force the process back into step 1. The reset button only works when the system is stopped. So now I'll hit reset. The reset button can be used in the case that a part needs to be removed from the conveyor for whatever reason. Well, there you have it, a Pico Smart Relay conveyor control project.